Dear student, welcome to class of location-aided routing. In this lecture, we will discuss about the new technique that would be used by the routing protocol in wireless network. So, as we discussed in our last lecture, that we can go for flooding, then onward control flooding based on flooding of control packets. And now we will actually do the minimization of that space in which we will flood our control packets. So we start this lecture, and here you can see that in location aided routing, we actually exploit the information to limit the scope of the route request flood, that how far this flooding request will be forwarded or disseminated inside a network. Remember that we can obtain the location information about any nodes either by GPS, or sometime the respective node can share with other nodes as well that what is his new location. So the important thing that we should know about that what is the speed of a node, and what is the direction of node, so we can actually draw this expected zone. So for example, if this is the network, and there are different types of nodes inside this network, and our destination node is a mobile, and it's moving from one location to another location. For example, the destination node is moving from this location to this one and then onward here. So instead of forwarding our packet, our control packets throughout the whole network, we forward it based on the specification we have about the XYZ plane of our network. For example, if we flood a packet inside the whole network, so we actually disturb 100% nodes that are part of this network. For example, if we flood across this whole network, then every node will forward those packets to find the destination node. But for example, if we know that our desired destination is at this point, for example, at this point, then we can restrict our flooding mechanism to this particular region. So here you can see, for example, if we divide this network into equal parts, then we only forward our flooding request in 50% region of this network, and 50% node, or even less than 50% node, will utilize their energy, will utilize their resources to find the destination node. Similarly, if we have a look to this distribution as well, in this situation, we are only disturbing or flooding the route request in 25% region of the network. And this only happens, or this is possible because of the location that we know where our desired destination node is. To get the information about the destination node, info about our desired destination, so the first approach is that we can use the GPS to obtain the location. Obtain the location of our desired node. Another one is that the destination node broadcast its XYZ position. Broadcast its XYZ position to all nodes that where he is. Or similarly, we can also calculate the expected zone where the node could be based on the direction, in which direction the node is moving, and similarly based on the speed, and then onward the mobility model. If, for example, he is going in a straight line, so we can easily draw the expected zone. For example, here you can see, for example, if this is the network region and a node start its mobility from here, and its speed is, for example, 1 kilometer per hour. So this direction is actually east, west, north, and south. So this direction is actually towards south. And after 2 or 3 hours, he will be 2 or 3 kilometer away towards south side. So that's why it is very important to know the speed and the direction And for example, if the direction remain the same, so we can calculate after 4 hour, after 5 hour, after 6 hour, and so on. And whenever there is any change in direction, then similarly, we will follow the same approach that where the direction was changed, then we can calculate the expected location. So for example, the expected location after 2 hour, this is expected location of a node. This is expected location of a node after 2 hours. Similarly, for example, this is the expected location after 4 hours, and then onward 5 hours, and so on. So you can easily calculate that what will be the expected location based on the speed and based on the direction of any node. So now moving toward the next phase. So expected zone is actually the place where we can find out the node. Similarly, you can define the expected zone based on the mobility pattern of the node. So now moving next toward the slide, and here you can see that expected zone is actually determined as the region that is expected to hold the current location of the destination. So it is actually the place where you can easily find the node even after mobility. This region is determined based on potentially old location as well as the knowledge of her destination speed. As I told you earlier, that you should know about the old location of the node and then onward in which direction he is moving. Route request limited to the request zone should contain the expected zone and the location of sender node. So it is very necessary to know that we can restrict the flooding of control packet or request for a route discovery in that particular region. And we can avoid all those nodes which are not part of this expected zone. So this is a very good way where we can reduce the energy utilization by not involving all those nodes which are not relevant with respect to the destination node. So this can also help us to increase the network lifetime. You can also have a look over here to the expected zone where we have X, which is the last known location for node D. And here we can also have the Y, which is location of a node D at current time, that is T1. So T0 and T1, then we also check the radius of node X, that what is actually the zone. And over here you can see that we actually have a circular range or zone for node X, and for our destination node that is actually drawn from a node X. So this is the radius of this circle you can see over here, and now we will forward, we will flood, we will broadcast the request for the route toward destination node here in this region which is defined. So here you can see that what is R, or how we can calculate it. R is actually the radius of the estimated zone for node D. And here is the formula. R is equal to T1 minus T0, where T1 is actually the time for new location, and T0 is actually the time for older location. At T0 where the node was. So how much time actually passed while the node start movement or mobility from that location. And here is the speed, the estimated speed of node D, which is the desired destination, that how far the node D will be from the base station or from the base position. So here you can see that how we can actually derive the request zone from the network space. So network space is the space of the overall network which reside all those nodes, while the request zone is very limited and it's up to the speed and the time that we defined to know about the destination node. So here you can see that the requested zone can be less inside than the network space. The maximum size of the request zone, or we can say the expected zone, is the network space, the overall network. So gradually you increase the size of a network zone or expected zone when you didn't find a node inside the defined XYZ plane. So here in this diagram, as you have seen, that we have three types of node, A, B, and S. And these nodes within the request zone will only forward the route request. So here, as we defined the route zone, where node A doesn't forward route request, but node B does. And reason behind that is that node A doesn't come inside the request zone or expected zone, while node B forward that packet because it comes inside the request zone. So it means that the expected zone is also shared with all these nodes, and similarly all these nodes also know about their position. So request zone explicitly specified in the route request, and each node must know its physical location to determine whether it is within the request zone or not. So this is very easy to determine by getting the expected zone XYZ dimension, and then onward check your own dimension that either you lie inside that expected zone or not. So those nodes which are inside the request zone or expected zone will forward the route request. If route discovery using the smaller request zone, as I told you earlier, for example, if we have defined a request zone over here as we did in the last example, for example, this is our network space, and we define a network zone over here in this region, and this is the source node, but we are unable to find the destination node in this network zone, our expected zone. So therefore we will increase the size of a network zone or expected zone. And similarly, if we are unable to find it here, then onward we will further increase it over here. And at the end, the maximum thing is that over the complete network space will be added inside our expected zone. So we will increase the size of expected zone as we fail to find the destination node. So same thing he actually discussed here. If route discovery using the smaller request zone fails, then the sender initiate another route discovery after timeout, and that's probably had the or have the larger request zone. So the larger request zone means that there is more opportunity or more probability to find the destination or the desired destination node. And the remaining process of the location aided routing protocol for the route discovery is similar to dynamic source routing protocol that we discussed in last lecture. Now here we have some variation in location aided routing, and the first variation is the adaptive request zone. Adaptive request zone means that we can define the request zone based on our requirement, and similarly it can be changed. There can be some modification as per the requirement of the destination node. In adaptive request zone, each node may modify the request zone included in the forwarded request. Then the modified request zone may be determined using more recent or accurate information and may be smaller than the original request zone. And here you can see, for example, if we have found that desired destination. Let me take this example again, the same example again. For example, we have defined this line as an expected zone, but later on we find that the destination node or the desired destination node is somewhere close to the node. So therefore, we will actually limit it to that point where the desired destination node is. And we will not cover this area which was earlier defined in the expected node. So that's why the author is trying to say that the modified request zone may be determined using the recent and updated information, as we find in the example that node D is closer to the source node, and therefore we should redefine the expected zone in which the new defined expected zone is per the updated information will be smaller in size than the original zone. Here you can see in this example, here is the request zone adapted by B over here, and here is the request zone defined by S. So almost till this region, you can see here that this region is not covered inside this zone because it was already defined by sender node S, and now the request zone actually adapted the new zone which is defined by the node B, and now it will forward its packet or messages or the route request within the domain or zone defined by node B. Another variation is implicit request zone, as we have discussed in the last scheme, where the route request explicitly specified a route zone based on the updated or recent information. So another approach over here that can be where a node X forward a route request received from Y if node X is deemed to be closer to the expected zone as compared to Y. So now here, every node is know about the position, his own position, as well as know about the expected zone or expected location of node D. So therefore, he will only forward a packet once he came to know that he is closer to the destination node, and his forwarding will definitely help this frame or this packet to get the destination node. The main motivation behind this is to bring the route request physically closer on each clock pulse to the destination node. So on each clock pulse, whenever there is forwarding, the route request will be getting more closer to the destination node. This is very important, and it is also considered as one of the important parameters that on each clock pulse with each move, the sender request or the sender data should be closer to the destination node. So the basic proposal in location-aided routing initially say that location information for node X become known to Y only during the discovery time or the discovery process. So therefore, the location information is used for future route discovery as well. Remember, particularly in ad hoc network and mobile ad hoc network, the nodes are able to move and change their position time to time. So therefore, we need to update the location information, and then onward, once the location information are updated, then we should start the route discovery process. Because every route discovery process yield more updated information, which is used for the next discovery as well. Here are some advantages and disadvantages, pros and cons of location-aided routing. And as you can see that with location-aided routing, we have another mechanism that we reduce the scope of route request flood. And it definitely helps us to increase the network life and increase the reliability and improve the resource utilization of the network nodes. Similarly, it also reduces the overhead for route discovery. So overhead is actually the additional charge which is paying by the network in terms of resource utilization, in terms of time, in terms of bandwidth consumption, in terms of energy consumption. So it is also reduced by reducing the discovery zone to the expected zone based on the movement of the destination node. Disadvantages of LAR node are definitely here, and some of them are listed here, out of which number one is that every node should know about their physical location. And sometimes it is very challenging that the node should know about its current location, specifically when it continuously moves from one location to another location. We will also discuss some localization techniques in which we would be able to learn that sometime nodes may take help from its neighborhood nodes or surrounding nodes to get its own location. Another disadvantage that it doesn't take into account the possible existence of abstraction for radio transmission. So sometimes there is possibility of a certain abstraction that comes between two different nodes. So from GPS perspective, as you are looking from the top, you may find that they are close with one another, but actually there is an obstruction between both nodes and they are unable to communicate with one another directly because there is any medium which is not means which is not capable to penetrate from any side, either from source side or from destination side for communication. So therefore, sometimes there may be lapses such as abstraction, which couldn't allow two nodes that they can communicate with one another. Now we would actually discuss different types of protocol that works on these mechanisms. And one of the most important protocol that we will discuss is the DREAM protocol. And DREAM protocol, actually, DREAM stand for Distance Routing Effect Algorithm for Mobility. So this protocol, DREAM protocol, actually use the location information as well as the speed information of any node to find its location, and it works based on LAR protocol. The DREAM also uses flooding of data packet as the routing mechanism. So remember, this is not the control, it is the data packet that is used by the DREAM. So there is possibility of exposing some information or some confidential information of a node to some intermediate nodes. DREAM also uses the location information and also limit the flood of data packet to a small region. And remember, this region is defined based on the speed and based on the direction of this destination node. Here in this diagram, you can see that Dream actually allow nodes to make a cone-like structure to discover the expected destination or the desired destination. And here you can see that mostly source S know about all the surrounding neighborhood nodes. Therefore, he know that his desired destination is not here in his particular zone. So therefore, he actually narrow down this search close to his neighborhood, and it getting wider as far as the nodes or the route request is moving away from the source node. So here you can see that this search is getting wider as the distance with the source increased. So node A in this example, on receiving the data packet, will forward it to its neighbor within the cone rooted at node A. So here the expected zone is in the form of cone. It is not in the form of circle that everyone will receive, but it is in the form of cone, and it is some sort of very specialized operation toward that particular direction in which the destination node moved earlier. So sender node S will send the data packet to all neighbors in the cone routed toward node D. So its data is also forwarded, and therefore there is some chances uh, of misuse of this data, or intervention by any other node, or some sort of tampering may happen. So the expected zone you can see here is this cone for node D, and node S actually start its route discovery process from here through node A, and node A further extended to the desired neighborhood and then get the destination node. In Dream protocol, the nodes periodically broadcast their physical location. As I told you, that there is also possibility that every node should share its own location with the surrounding nodes. So therefore, the nearby nodes are updated more frequently than far away nodes less frequently. And as you know about the example, that as a node is far away, then it seems that its position is not changing very frequently. So here is a very good phenomena in which the distance effect is found, where far away nodes seems to move at a lower angular speed as compared to nearby nodes. And you can also take the example of aeroplane, that as much the aeroplane is far away from a human being, so it seems that the angle with the human being is changing. For example, this is a human, and here is an aeroplane moving in this direction. So for example, if this plane is closer here to the destination node, then the angle with respect to this node will be changing very frequently as compared to this node. So the change inside the angle, or you can say that the position of this plane with respect to this user or this human doesn't change very quickly as compared to a plane which is closer. So here, when it's close, the position of this node will change very. The position of a plane will change very quickly. So it is very important to know about this distance effect. So location updates time to live field used to control how far the information is propagated. So it is very important that this protocol is using the TTL field as well, that how far this information will be propagated. It can be based on the number of hop. It can be based on the time. So here you can see in Dream protocol, it also estimates the distance between source and intended destination in terms of hops. So the TTL field will definitely carry out the number of hops, that how far a node D is far away from the source node. So sender node send a route request within the time to live, that is the TTL, equal to the above estimate. So actually in TTL, we will put the number of hop as a parameter to get the desired destination. So hop distance actually estimate based on the physical distance that the nodes may have traveled since the previous route discovery, and then onward its transmission range. Now moving toward the next protocol, which is based on the geolocation or geographic location of node. The protocol is GDR, and that is geographic distance routing protocol. Here in this diagram, you can see we have again the source node and many other nodes in between, and the destination node D. Here we will also explain the abstraction. You can see here in the black color that there's an abstraction which actually stop these nodes C and G to communicate with node D, with node E. So location of the destination node is assumed that it's known, and it is also shared with the desired sender nodes or the neighbor nodes. Similarly, each node also know the location of its neighbor, so therefore they also share these information with one another. Every node will forward a packet to its neighbor closest to the destination node. So therefore, every node will try its best to get closer to the destination node on each movement on each clock pulse as they forward data toward destination node. So therefore, S forward the data to B, B to H, and then to node D. And you have seen in the diagram as well that node S actually use node B and H to deliver its data to the destination node D. The algorithm actually terminates when the same edge is traversed twice consecutively, and you can see here in the form of twice triversion here between C and G. C send it to G, and then onward G send it to C. So the algorithm actually fails here between S to E. Algorithm fails to route from S to E. And the main reason behind that is that node G is the neighbor of C. Node G is here, that is the neighbor of C, who is closest from the destination E, which is over here. But C doesn't have a route to E, as C doesn't have the route to E. So therefore, this is the abstraction which actually stop communication between C and E. And automatically, when this link is traversed twice, the algorithm will stop working. So we have only this option, though in case we can remove this abstraction between C and E, then we can be able to communicate between C and E. And we also would have this option to communicate with the node E and D through S, B, C, E, and D. Now we will discuss about the broadcast storm problem, which is a very common problem inside these wireless network. And sometimes because of this problem, the packet collide with one another, or the frame collide with one another, and they drop and no one actually, and they drop this data and no one receive the data packets, or even if they receive those packets, there will be some error inside those packets. So here in this diagram, you can see we have this particular topology to explain the broadcast storm problem. We have node A, B, C, and D, And when node A broadcasts its message, a route query to node B and C, so both of them actually receive that query. And then in next clock pulse, when B and C forward their query to to their neighbors, then D is actually their neighbor. So B and C actually transmit their route request in the same clock pulse. So therefore, there is possibility that their packet may collide on the reception antenna of node D. So they are reacting to receipt of the same message from A, and then onward after reaction, the collision actually happen at node D. So when B and C transfer a packet at the same time, as you can see that the distance from D to C and D to B is almost same. When they do the transmission at the same time, there is higher probability that the packet reaches node D reception antenna at the same time, and it results in the collision as a destruction of packet. Another important problem can be that, for example, even if there is some intentional delay created by either node B or C to forward their data, so it will create some redundancy where the node may receive the same packet, node D will receive the same packet twice. And though a single packet is sufficient to decide about that data, but he is receiving the same packet twice. So for example, if we can talk about one packet, then we can definitely ignore that. But if we are talking about thousands of frames that B and C forwarded to node D, then we can't ignore it because it will definitely create some more burden or more hurdle for node D and can be a threat for its life. Node D may receive from both node B and C, and therefore there can be a problem of redundancy. So now to solve this broadcast ROM problem, let me explain this on the whiteboard before going onward. That for example, here node A is sending to node B and node C. So he sent a packet 1 over here. Similarly, he also sent packet 1 to node B, node C. And now when node C will forward this packet 1 to node D, and there will be collision of these packet on node D. So there is possibility of collision on node D. In another scenario, node A forward the same packet to node B and C, and as you know that that node and as you know that even there is some intentional delay added by node B and C, so node D will receive the same packet twice. Once from B, one is received from this direction, node B, and another one is received from this direction, node C. So here you can see that there are two frames actually received at node D. That sequence number is 1. So now moving toward its solution. The first solution for the broadcast ROM problem is probabilistic stream that simply take the decision on probability. On receiving a route request for the first time, a node will rebroadcast, and in that situation, the probability will be highest, that is P. So the highest probability in this situation will be 1. And now, if the packet is coming again, also rebroadcast by different node should be staggered by using a collision avoidance technique that is wait a random delay when channel is idle. As we discussed earlier, that you can also add some random delay inside node V and C to stop this collision. So therefore, it would reduce the probability that node B and C would forward a packet simultaneously in previous example that we discussed earlier, that on the first time the probability is higher to forward a packet, and then it gradually goes down uh, when you are receiving the same packet again and again. Another solution here is the counter based scheme, where if a node, here you can see in this example where they have introduced two more nodes E and F. So for example, if node E here more than k neighbor broadcasting a given route request before it can itself forward it, then node E will not forward the request. This is a bit intelligent approach followed by node E. And it simply means that if you know something, it means that your neighborhood also have all those information, because in wireless network we are actually doing the broadcast communication or flooding. So therefore a packet received from a neighbor by any node means that they actually have some information about these nodes. So therefore, here the intuition they have added that k neighbors together have probably already forwarded the request to all of E's neighbor. So if E is receiving some information from F, from B, and C, then it also means that they have forwarded information to node D as well. Look at this. You can see that E know that B is a neighbor with node D and node F. So therefore, E should not forward the same packet to node F and node D. Similarly, C received the same packet from E received the same packet from C, and E knows about that node C has neighbor F, D, and E. And when I am receiving the packet from node C, so it means that it is already received by node D and node F, as it also comes in the neighborhood of node E. So therefore, node E will keep silent, not to create extra traffic inside the network. So this is another important technique that is followed, an intelligent technique you can say, that is followed by node E to stop extra overhead or to bring extra packets on the network. So broadcast problem actually create some issues sometime, that is collision and redundancy. Flooding is used in many protocols such as DSR, and similarly the problem associated with this flooding, as we discussed earlier, the broadcast from problem is the collision and redundancy. The collision may be reduced by jittering, by adding some intentional delay for random interval before propagating the flood, while the redundancy may be reduced by selectively rebroadcasting packets from only a subset of the nodes. So redundancy is actually controlled, that not to allow all nodes to forward the packet or data they receive. You should stop some of them, and you can decide that you can select some nodes among multiple nodes, that only they will forward their information to the next node or the neighborhood node or to the desired destination. Next is the AODV protocol, and we will discuss it from next class. So that's enough for today's class. If you have any question, you can ask. Thank you so much.